Okay, so in this section 8.3, we're going to look at the inverse of a square matrix. So let's recall that if I just have real numbers and I want to solve for x, we think about dividing by a, but really what we're doing when we're dividing by a is multiplying by this, what we call the multiplicative inverse of a. Okay, so that's a to the negative 1, of course, is 1 over a. And then I get this solution for my x. And so this A inverse I mentioned is called the multiplicative inverse, and anytime I multiply A inverse times A, I should get 1. Now we want to think about this definition in terms of a matrix. So if I talk about it in terms of a matrix, the I sub n is our identity matrix. Remember, identity matrix is a square n by n matrix that is written in reduced row echelon form. And we saw that if I multiply A, no, we didn't see this, but we now know that if I multiply A times A inverse, I should now, the multiplicative inverse for matrices is the identity matrix. And I can do it in either direction, okay, and get this identity matrix. And we read this A to the negative 1, we read this A inverse. Okay? So this is read A times A inverse is equal to I sub n, and A inverse times A is also equal to I sub n. So if I have two matrices, A and B, and I want to show that they are inverses of each other, I have to show both of these things whole. I have to show that A times B is equal to I. In this case, it would be I2 since I'm looking at a 2 by 2 matrix, and B times A is equal to I. Okay. So if we recall, I'm going to just do this one and this one only. When I'm doing matrix multiplication, I do the first row times the first column. First, we got to check to make sure we can multiply these by each other, and of course we can. Okay, and so I would have negative 1 times 1, which is negative 1 plus 2 times 1, which is 2. And I continue this, and I will get here, the first row times the second column will be a positive 2 minus 2. That's this term here. Then I do the second row times the first column, negative 1 plus 1. And then the first row in the second column would be a positive 2 minus 1. Okay. And what do I get? I get 1, 0, 0, and 1, which is I2. And so I am happy. Okay, and so here it is worked out for us, and we can clearly see that it equals the identity. But I have to do it in both directions. I also have to do B times A. In doing B times A, I see that I also get the identity matrix. And since A times B is equal to B times A, then we say that A and B are inverses of each other. Okay, so keep in mind, to have an inverse, you must be a square matrix. So to have an inverse, you must be a square matrix. But not all square matrices will have an inverse. Okay, so just because you're square doesn't mean you'll have an inverse. But to have an inverse, you must be square. So we have a little bit of terminology. If a matrix has an inverse, then we call the matrix invertible. So invertible matrices have inverses. Okay? Another word for that is non-singular. Okay? If it does not have an inverse, we call it singular. Okay? And as I mentioned before, a non-square matrix cannot have an inverse. Now keep this in mind, because why is this true? If I'm multiplying A times B and the orders aren't the same, and I have an n by n, when I flip the orders, okay, they may or may not be equal, so therefore I can't multiply in both directions to get the identity matrix. And so I also mentioned that not all square matrices have inverses. However, when a matrix does have an inverse, it is unique, meaning that there's only one inverse for a matrix. So in the first example we saw, we were given two matrices and we wanted to show that they were inverses. But how do I actually find the inverse of a matrix? Okay, I'm going to use this process that we see here. So if I have an n by n square matrix, right, I am going to augment it, and this is called double augmented. I'm going to augment the matrix A with the identity matrix. We've been augmenting with just the solution matrix, if you recall. We've just been doing this, but now I'm going to augment it with the identity matrix. Then my goal is to get this into reduced row echelon form, which means that I'm going to do Gauss-Jordan elimination, and our goal is to get this A to become I, which is my reduced row echelon form. So I want this to turn into the identity matrix. If I can get it into the identity matrix, then the resulting matrix here is the inverse. If this cannot become the identity matrix, then we say the matrix is not invertible or it is singular. Okay, and once I found that inverse, we always want to check our work. So let's find the inverse of this matrix A here. The first step, it says I am going to augment it with the identity matrix. Okay, so we call this a doubly augmented matrix. Now I apply Gauss-Jordan. So this is my doubly augmented matrix. I apply Gauss-Jordan. My first goal, of course, is to get this to be A0. So I can add row 1 and row 2, and then I get these results here, 0, 1, 1, and 1. The next thing is, I notice I have my stair-step pattern and I have my leading ones. I now have to get this 4 to become a 0. So I can do -4 row 2 plus row 1. And then I have the identity matrix. Okay? If I have the identity matrix, then what I have here, this matrix here, is now the inverse of my matrix A. So we see I start off with A augmented with I do Gauss-Jordan elimination and row reductions and get I A inverse. And we do this procedure for any square matrix to help us to find the inverse. Again, if I cannot get this into a reduced row, into Gauss-Jordan elimination or to the identity matrix. So for instance, maybe this row goes away, okay? Then that means that this matrix does not have an inverse. And anytime you want to check, you always want to go back, and I won't do the checking on this video, but you always want to go back and multiply your A times your A inverse and your A inverse times A, to make sure that you get the identity matrix. Now we're going to look at this example here and go through it with a 3x3 and find the inverse of this matrix. So our first step in going through this, and we're going to work through this one together, so work along with me, is we have to augment the matrix A with the identity matrix. And now we're going to go through row reductions to get to Gauss-Jordan elimination, or I, on this left side. So the first two things we want to do is we want this 1 and this 6, of course, to become a 0. So how can I do that? To get this 1 to become a 0, I can do negative row 1 plus row 2. So my first row remains the same. Now keep in mind, whatever we do to one side of the augment, we have to do to the other. So I'm going to go through this step together, and then I won't go through it individually each time. Okay. So if I do negative 1 times plus 1, I get a 0, which is what I want. This becomes a positive 1 plus 0, which becomes a 1. And this becomes 0 plus negative 1. Okay. But I also have to do it over here too. So this is negative 1 plus 0. Okay. And then 0 and 1 is 1, and 0 and 0 is 0. Likewise, we're going to do, to get rid of this 6, a negative 6 row 1 plus row 2. And then the resulting values are 0, 4, negative 3, negative 6, 0, and 1. And so now, again, we're getting this in the Gauss-Jordan elimination. So we need to get rid of, I notice I have a 1 here, so I need to get rid of this 4. Okay. Getting rid of this 4, what can I do? I can do negative 4 row 2 plus row 3. So my first two rows will remain the same. Oops, sorry. Okay, but now if I do these operations, this last row becomes 0, 0, 1, -2, -4, and 1. I notice I have my stair-step pattern. So now I have Gaussian elimination, which is in row echelon form, but we want it in reduced row echelon form. Okay. So I can get rid of this -1. How can I do this? I can do, looks like just row 2 plus row 1. And I'll get 1, 0, -1, 0, 1, 0, and then my other rows remain the same. Okay, we're going to move up here. And so what would my next two steps be? I now want to get this -1 and this -1 to be zeros. So let's do so. Okay, my first row, I can do row 3 plus row 1, and I'll get 1, 0, 0, -2, -3, 1. Okay, my second row, I can also do row 3 plus row 2, and I'll get 0, 1, 0, -3, -3, 1, and my last row is going to remain the same. So what do I notice? I now have the identity matrix, and since I could get it into the identity matrix, it is augmented, with a inverse. So what is a inverse? A inverse is the matrix -2, -3, 1, -3, -3, 1, and -2, -4, 1. Okay, and you can check this by multiplying A times A inverse. It should equal A inverse times A, which should be the identity matrix of 3 by 3. Now we see that Gauss-Jordan elimination worked for either the 2 by 2 or the 3 by 3. Okay, but it can get a little tedious with as it gets bigger and bigger. You won't have to do a much larger, probably than a 3 by 3 inverse. Okay, but if I have a 2 by 2 matrix, okay, there is a different method we can use instead of Gauss-Jordan elimination that might be a little easier for us. Okay, and so it's a simple formula that we're going to use if I have a 2 by 2 matrix. It only works for 2 by 2s. So if I have this matrix A, okay, then the A inverse is going to become 1 over, so this is a scalar, I'm going to multiply these entries here, A times D, and I'm going to subtract away these entries here, B times C. Okay? And this is going to be a scalar times a new matrix where I am going to switch A and D. And so when I switch A and D, it becomes D and A. And then I am going to make these two values negative, -B, -C. And this becomes the inverse of my matrix. This part here, AD minus BC, we're going to give it a name. This is what we call the determinant. And the determinant is going to be very useful for us as we go through and continue to solve things using matrices. It's going to give us a lot of information. But the first thing we know that it gives us is the inverse of only a 2 by 2 matrix. So I do want to note that because we have this in the denominator, if it equals 0, of course I can't have 1 divided by 0. So if this determinant is actually equal to 0, then I know that my 2 by 2 will not have an inverse. So it says A is invertible if and only if AD minus BC is not equal to 0. Okay. And as I mentioned, this AD minus BC is going to be called the determinant. So let's find the inverse of these matrices if they're possible. So looking at matrix A, the first thing we always want to do is check to make sure that my determinant is not equal to 0. So in this case, A times D is 3 times 2 minus C times B, or B times C. Most places commutative is okay. And then what do we notice? Okay, it equals 4. So yes, we have an inverse. So now let's set up this formula and plug in 2. Okay, so we do 1 over 4, which is this determinant. Okay, and let's hold on, let me pause. So I want to recall first, this is the the equation for the inverse. Okay, and we check to see that this was not equal to 0, it was equal to 4, so I do 1 over 4. And then how do I get this new matrix here? I change these two values around. Okay, so this was a 3, this becomes a 2 and a 3, and I switch, and then I make these other two, which was -1, negative. So a negative of a -1 is a +1, a negative of a -2 is a +2. And this is just scalar multiplication. I can multiply in my scalar, and then I get this resulting matrix. And this becomes my A inverse. Okay, so now if we look at matrix B, so this was our original matrix B. We got to check that determinant. Okay, so checking the determinant, we do 3 times 2, which is 6, minus -1 times -6, which is a +6. So I get 0. So that tells me that B is not invertible. And what does that mean? B does not have an inverse. So let's recall that if we have a linear system of equations, it's going to have either exactly one solution, infinitely many solutions, or no solution. And so if the coefficient matrix, keep in mind the coefficient matrix are the coefficients of the variables, is a square system. That means we have the same number of equations as variables or unknowns, okay, and it is invertible, then the system has a unique solution, which is meaning that it only has one solution. And what is that unique solution? Okay, it's going to be defined as follows. If A is an invertible matrix, if A is an invertible matrix, then the system of linear equations represented by AX equals B has a unique solution given by this here. So where does this come from? If I multiply A inverse by both sides of my matrix equation, okay, then of course this equals I, and I times X, the identity matrix, just gives me X is the A inverse times B. Okay. So let's solve this system of linear equations using the inverse of the matrix. So you might notice that this is the first matrix, matrix equation we looked at. But this is also the AX is equal to B here. So let's write the matrix equation. The matrix equation would be -1, 2, -1, 1. Okay, this is my A. My X in this case is XY. Okay, and my B is my 2, 1. And so we actually saw earlier that the inverse of this matrix is 1, 1, -2, -1. If you go back to your first slide, you will see this matrix inverse. So if I want to solve for X, now all I'll have to do is multiply this inverse matrix, 1, -2, 1, -1, times my matrix B. And matrix multiplication is actually a lot simpler than the Gaussian elimination, the substitution, all the methods we've been doing in the past. Okay? And if we multiply this through, this is a 2 by 2, this is a 2 by 1, so I should get a 2 by 1. And what do I have? The first times this, I have what? 2 plus -2. And did I write this right? Oh, no, did I write the right one? Yes, sorry. And then I have 2 plus -1. And so the solution to this system, and I see the problem. That's the problem. Sorry, guys. We're going to change this. I noticed that I left a negative off. So this should be a negative here. And so this should be a negative here. So let's make some changes to this whole system. I apologize. Now let's see. Now I have 2 plus a positive 2, negative 2, and then I'll have 2 plus this times this is another, in this case, positive 1. So the solution to this system would be 4, 3. Right? And so this is another way, this is now a 6th way we can solve a system of linear equations, but now that has a square coefficient matrix.